Good morning, everybody. I'd like to welcome you to the ATIYA lectures, which will be webcast live. So that's the first thing I should tell you, that we are on air. And I'd like everyone to switch off mobile phones if you have them on at the moment. There's seats at the front. When people are coming in, I'd encourage you to take the seats at the front. This lecture will be the first in a series of lectures or events that will unfold throughout the year and will be announced as and when they happen. Today's lecture will include excerpts from a lecture that Sir Michael gave at another event at the Royal Society earlier this month. So at some point there'll be a switch to a previous lecture. So since we are being filmed and this is a filmed lecture, this could be the beginning of an infinite series of filmed lectures that are filmed and transmitted. Before I hand over to Sir Michael, I'd like to briefly say a few words about him. He doesn't need an introduction, I'm sure, to most of you. Sir Michael has shaped and influenced many parts of mathematics. He's won the highest recognitions you can wish for in mathematics, starting with the Fields Medal and going on to the Abel Prize and many more in between. He has been interested in theoretical physics and worked with many physicists, particularly in the last 20 years or so. I've had the great privilege of discussing various areas in physics with Sir Michael, and I know that his ideas are always insightful, fresh and provocative, and I'm sure the same will be true in today's lecture. So I'll hand over to Sir Michael Atiyah.
Thank you, Bernd. If you don't mind, I will remain seated. My age is a luxury one can afford. I want to make first just 2 points. As you've heard, I will be showing some video of the lecture I gave at the Royal Society of Edinburgh, the one on Maxwell. And on that occasion I said a few things which were mildly provocative, but I kept it rather low level, didn't trumpet it around, it wasn't a suitable occasion. This time I'm going to be much more brazen. I'm going to make some very radical proposals, and I'll shout them loudly from the rooftops, so nobody's under any illusions that these are radical, but they're also exploratory. I can't guarantee everything I say is correct, but it represents a lot of thought from me and my collaborators, and it's meant to be a sort of program to be worked on for the future, and I hope many people will be involved with that. So I will also, of course, later on give more detailed thanks to all my collaborators, all the people around the world who work in these fields, and I'll give some references to provide exact backgrounds. So now I'm going to start with the video, which has been taken from the Royal Society of Edinburgh lecture, but has been truncated a bit, so it'll be jagged at the beginning. Let's start with some elementary geometry. Turn the volume up. Now here is a picture which you might recognize. It's drawn on the plane, but you imagine it's a projection from 3 dimensions, and what you see is a projection of a cone, 2 cones, one on each side, and cut by various planes. Along the bottom, if you cut that by a plane, you get an ellipse. Well, you get a circle in that form, but if you tilt it, you'll get an ellipse. Along the side, you'll get a hyperbola. The one I've drawn is the most perfect hyperbola, but if you tilt that, you'll get hyperbolas with different shapes. And along the edge, there's the lines which are tangent to the cone. They cut the thing into parabolas. So the hyperbola, the ellipse, and the parabola, which are very important things in mathematics and physics, are all seen there in a very simple picture. I hope you're still with me. This is not going to get much more difficult. Now here I talk about directions. You imagine you starting off at the point 0, then you can go in 2 different ways. You can go to +1, or you can go to -1, and you can go, that's what we call real numbers. And +1 and -1, well, they all go back to somebody called Robert Record, who invented the equal sign, and you could say the equal sign was the beginning of algebra. And then, but instead of going from just a +1 and -1, you can remember there are these complex numbers, which you already had a class on from previous speakers. You can go up to I, or you can go to -I. Already you've got 4 points round about 0, which you can think of as standing up in different directions. Then, actually, going on beyond complex numbers, you have the ideas introduced by Hamilton, the great mathematical physicist, who discovered the quaternions, where besides having I, you also have J and K. And there you have, in a nice diagram, all the great contributions of the mathematicians of that era. And if you think of those dots as standing up in space in different directions, if you're a chemist, you can think of those as the locations of atoms. You can think of those of your chemists might recognize the sort of molecule for salt, or if you're other kind of chemists, you might recognize methane. These are templates for chemistry. And I mean, I say they're templates, I really mean they're templates. This is not just some fiction, not just mathematical symbolism. You can imagine that as being exactly what you see in the laboratory. And then we move up to the geometry, dimensions. Well, on the left-hand side, I've written down the dimensions. We all start off living on a line. We've gone from the positive real line to the negative. We have the real line, which is plus and minus. We moved up into the complex plane, as you heard, where we have the circle of rotations. And you can go up into higher dimensions, three-dimensional space, where the boundary is two-dimensional sphere, and the four-dimensional space, with the dimensions go up one at a time. And Hamilton was trying to go beyond the complex plane to do something in dimension 3. He realized that you had to do 3 and 4 together. That was his great insight, which is recorded somewhere on a bridge in Dublin. So this is the history of dimensions in mathematics, and it has great impact in physics, because as we've already heard, the complex numbers play a very important role. Now I go on to equations. As you know, mathematics depends on being formalized in terms of equations. And the equations, of course, use the algebra. Algebra was a great contribution of the Arabs. Something goes back into India and the Chinese. And I've written down here some very important equations. These are second-order equations. They involve squares. So the second line says x squared minus c squared t squared equals 0. And you can recognize in there, well, anybody will recognize what you want. Speed of light, c, and so on. And you can recognize that it also factorizes into x minus ct and x plus ct, which is Dirac's contribution. The c squared is the number that appears there, can vary from -1 to +1. And as it goes through that, it goes to a singular point when c equals 0, which is what physicists call a phase transition. X and t can stand not only for one variable, for many variables. X can stand for a whole string of variables, as many as you like, x1 and xr, depending on what dimension you're in, and t can similarly stand for t1 to ts. And c, similarly, will be paired off with that, has also to have the same number of variables. All this is elementary algebra, but it's the algebra that underlies the equations of physics. The second-order equations, first of all, start off as algebra, but then they become analysis. The second-order equation most familiar to people is the Laplace equation. It's the example of what's called an elliptic equation because of the ellipse. Then there is the wave equation down the bottom, which is called hyperbolic because it reminds you of the hyperbolas. And on the way, you get what's called the heat equation, which is parabolic. It's one in which the second-order terms dropped out, and you're left only with a linear term for d by dt. Those are the fundamental equations of classical physics, and they correspond fundamentally to the basic bits of geometry that I told you about. All very obvious, all very straightforward. Everything knows, you all understand all that. You learned it at school, or you learned it this morning for the lecture. Now let's go make it easier. Let's go. That was quadratic equations. Let's go to linear equations. Everybody can do linear equations. So the first equation, if I factorize it, I would get x plus or minus ict. It's a linear equation between x and t and c. Again, x and c and t can be stand for many variables, but just think of them as one at a time. That will do. And then when you go to analysis, well, the analysis that follows onto that is precisely the Dirac equations. The Dirac equations are first order, unlike the Schrödinger equations and others which are second order. So the Dirac equations are first order, and Dirac had to introduce something to go with them. He had to introduce spinors. Now, I don't think spinors have been mentioned in the lecture so far, but they are fundamental. Spinors are to geometry, well, spinors are like the square root of geometry. So I ended up here with this catchphrase which is to be taken seriously. It's written in a nice big letters, you can see, with colours. The colours are not accidental. Who knows what those colours are? They are the colours of the rainbow, as you recognise them. You remember I was taught the anagram of Roig-Biv? Well, the Dirac is red, and you go down the spectrum of the colours until you get the geometry, and fortunately, the number of words in there is exactly the number you need for the rainbow. So take that seriously. The Dirac world is the square root of geometry, and the spinors are what live in the Dirac world. Without spinors, you couldn't formulate the Dirac equation. They are fundamental, and you know that it took mathematicians many, many centuries to understand what the square root of -1 is. The square root of -1, for those of you who don't know, or haven't learnt already this morning, is I, the complex number I, which was invented because they needed something for the square root of -1. So it took them hundreds of years to realize that not only was the square root of -1 useful, but in some sense you could actually make sense of it. And then gradually it became absorbed, became part of the foundations of mathematics. From there it became part of the foundations of physics. So these imaginary things acquired a reality. The same thing has happened with spinors, but that took much longer. Spinors are not the square root of -1, they're the square root of geometry. Now that's a much more difficult notion. Who knows what the square root of geometry means? Well, I've been working with spinors most of my life, and I'm old enough now to have had quite a long life, and I still struggle to understand what spinors are, but I think I'm getting near the end of the road now. I think I know what spinors are, and that's encoded in that word. And the Dirac word is the square root of geometry. That is what spinors are. They are fundamental things which precede geometry. Geometry is what, as you know, came from the word being measure the earth. That's what geometry was. It was more or less geodesy. Look at the earth, measure angles, distances. And Dirac's world is different. You introduce spinors, which are the square root of geometry, and if you don't understand what they are, you haven't understood Dirac, you haven't understood physics, and you haven't understood, but don't worry, very few people have. I think nobody has really understood what spinors are. We're only getting close to the end of the road now. I don't want to be premature, but maybe by the end of this morning, you will all be able to pass the test. What is a spinor? Now, the physicists know about two kinds of worlds. There is the non-relativistic world, and there is the relativistic world. You've heard about that from the two lectures this morning. Now, the non-relativistic world is the world of second-order equations. It involves metric geometry, which measures distances, curvature of space. All of these things depend on measurement. You can't measure until you've got a notion of geometry. Geometry is measurement. It means measuring the earth. Now, people have known for a long time that you can have a flat earth, which has no curvature. You can have a sphere, which has positive curvature. And you can have that other more mysterious thing, which is called hyperbolic space, which is negative curvature. Negative curvature is what when you're climbing a mountain and you get to a saddle point, a pass, one direction goes down the valley, the other direction goes up the mountain. You are at the saddle point. Saddle point is a space of negative curvature, where the two up and down go in different directions, as opposed to a maximum or a minimum, where you're going in the same direction. Symmetric geometry and curvature are fundamental in our understanding of geometry and our understanding of basic physics. The Laplace equation, by here, when I talk about the Laplace equation, you know the Laplace equation is the sum of squares of second derivatives. So d by dx squared, dt by squared, and so on. But you can put any signs you like in, then it changes its mind. Instead of being the Laplace equation, it becomes a hyperbolic equation, and those are what are called phase changes. So all equations, all signs are allowed. And then you come to things like spectrum. If you have a Laplace equation in nice situations, you will get a spectrum, what are called eigenvalues, and those are interpreted in terms of energy levels. You've seen pictures of that before. And closely related to that, you will of course get the notion of mass. Mass and energy spectrum go together. The mass is the embodiment of this story. And you've heard all the lectures this morning before me told you that in many ways. Mass comes associated with spectrum, which shows the energy levels, and so on. That's all part of the non-relativistic world. And the Schrödinger equation is the equation of quantum mechanics, which is again a second-order equation, but written in a non-relativistic way. All these equations mean that you've separated out space and time. They're all fundamental in classical physics, but then along came, of course, geniuses like Dirac. And in Dirac's world, we're dealing with a relativistic world. A relativistic world is linear. There are no second-order equations, they're linear. The geometry is no longer metric geometry, it's what we call conformal geometry. Conformal geometry is concerned with things like angles, areas, and so on, not with distances. Distances are metric, areas and angles are conformal. So when you go onto the Earth and you look at different latitudes and longitudes, you're really using conformal geometry. Conformal geometry is more, in some sense, more, how should we put it? It doesn't involve measurement in the sense of distance. Distances are not involved in conformal geometry. Dirac equation, similarly, is not concerned with distances. It's concerned with conformal stuff. The Dirac equation belongs to this linear world, and it is consistent with conformal theory. When people mention the conformal invariance of the Maxwell's equations, that was conformal invariance, which actually has a very interesting history. It was discovered independently by two people in Cambridge, and gradually realized that was important. So the Dirac's equations are conformally invariant, and coming out of that, the most important notion in a relativistic world is not energy, it is entropy. Entropy, or information, is the analog in the relativistic world of the non-relativistic notions of energy. Energy and entropy are intimately linked, but they are not the same. And the best example is because the lectures before me were so brilliant, they told you everything. I don't need to repeat things because they were so well explained. All I'm going to do is to look at them from a new point of view. And the next slide really is the only two slides you need to remember in this lecture. The one that's following and one later on. So the next one, if I get it right, is this one. Now look carefully at this one. Look carefully at it. This is the one that you have to remember. It is vitally important. Now what does it have in it? I've written down gravity. Because so far, as people have pointed out, in conventional physics, gravity is to a great extent ignored. When you do atomic physics, you don't worry about gravity. Gravitational force is so weak that it doesn't affect the nucleus or the atom. Mistake. It does. Gravity is all around us. We can't escape it. The reason we can't escape gravity is, as you know, gravity is only one direction. There is no anti-gravity in the obvious sense. So gravitational forces accumulate. And since the universe has matter in it, all that matter produces a gravitational force which is everywhere present. You cannot escape gravity. Only escape gravity if you go into a world where there is no gravity, where there is no mass. That's a very dull world. So you cannot escape gravity. Gravity is always there. It is background. You can't help it. So gravity is very important. And the one place where I'm differing slightly from my predecessors is to emphasize the fundamental role of gravity. It has to be there. Everything hinges on gravity. And I'll try to explain a bit more. Now, in the middle, I've got what is, well, you can take of it if you like. If you think of it one way, it's the Archimedes screw. Think of it the other way, it's the double helix. They're the same thing. Reflect on that. This is a picture, and there is a movie that goes in. You can get this on the internet. And now there is a movie version, but it was a little bit beyond the technology of my very able assistants. But it does actually show it winding round. Now, so let me digress a moment, since I have time. Let me tell you, what is the Archimedes screw? The Archimedes screw is, of course, named after Archimedes. But before Archimedes, it existed long in the past. If you go back to Babylonian times, there were the Hanging Gardens of Babylon. How were they watered? Think about it. How did you get people to get water up from perhaps the Euphrates, which is quite a way, up to Hanging Gardens. I'm not sure how far the Euphrates is from Babylon. I have to look at my geography, but I'm sure there are scholars here who know that. Well, the answer was that you use the Archimedes screw. And that was a device for pumping water from a lower level, the river, up to a higher level, which could be agricultural field if you're a farmer, but it could be the Hanging Gardens of Babylon. Of course, in those days, the energy to pump that water up was probably produced by slaves. You whipped your slaves harder and harder, and they pulled round and round, and eventually the water got up. So you turned the energy of the slaves into the entropy, which is driving the water uphill. So, of course, later on, Archimedes came along with a much better device. When I was a boy, I used to go on the Nile steamer down the Nile, and the Nile was a long way beneath the fields which where the peasants farmed. So they needed to get water from the field, from the river, onto their fields. So they would go down with buckets and come and carry up a lot of work. Archimedes' screw was a brilliant device. He put a wooden contraption into the ground, which was essentially this helix. The water down the river, the Nile, came down, entered the bottom of the spiral, and then the pressure of the water gradually drove its way up to the top, till it landed on the fields. Meanwhile, the farmer was sitting, smoking his narghili, enjoying himself, doing no work. He was being irrigated his fields for no cost. It was a most ecologically brilliant invention, long before modern ecology said we shouldn't be burning carbon and so on. There was no carbon. But where did he get his energy to pump the water uphill? It came, of course, from the Nile. The Nile was going downstream. Why was it flowing? Of course, because of gravity. If there would be no gravity, there would be no fall. The water would not be stagnant. It would not go up. So what the Archimedes screw was doing was converting the energy of gravity into the entropy required to pump water uphill. Simple as that. But it was a genius of Archimedes to realize that this is what you do. This is the shape that you have to employ to do it efficiently. This shape, in mathematical terms, has technical terms. It's called a conicoid or something like that. And it's a very remarkable surface. If you cut it open, it turns out to be the only other ruled surface on the plane that is a complete surface. And you have the plane and you have this thing here. This is a universal object, mathematically. It's absolutely unique. And Archimedes used that beautifully to transform gravity into entropy, driving water uphill. That was a stroke of genius. Archimedes was, amongst all my heroes, well, certainly a candidate for #1 slot. You know, you take a vote amongst public. Who is your #1 figure? Well, we can all have our heroes, Maxwell, Dirac, but certainly Archimedes is up in the top rank. And now, if you look down below, you'll see the word double helix. It wasn't until I started looking at this picture that I realized this is actually exactly a double helix, word for word. You look into it, the geometry of the double helix is all here. There are 2 strands of DNA going in opposite directions. If you're a molecular biologist and you just study this, you realize that Crick and Watson didn't have done that any hard thinking. All they needed to do was to go back and talk to their Iraqi colleagues who did archaeological digs in Iraq. And from that, they would have found it out. Well, I've got on the side here a picture of the Escher drawing, which shows you how you can convert water falling downhill by a bit of clever trickery due to Roger Penrose. And that is the trick, to convert the waterfall into, and there's a nice story with that, but I better stop because my time is running short. But don't forget this slide, okay? That's the most important slide, except for 1 or 2 little ones, which we're going to follow now. This one here. It goes through it fast, but basically, here is the Earth. Sorry, there's the Earth, and there's the Sun. They're connected by a little strand, and I've got colours to indicate. And this strand is actually what physicists call a string. People talk about superstring. That's the string. You start off with a world which is symmetrical at the beginning, and according to the basic idea of Dirac, the time flows to produce asymmetry. And these ideas are also developed by Kepler and Newton. Thank you. I hope you enjoyed that. Well, now I'm going to show you some slides which will supplement the topics raised in there. If I press the right buttons, we should get them. Let's see. Oh, it's on here. There we are. Right. So my first slide is there, and it's a question Einstein asked many years ago when people asked him, what do you think about all the new particles people are discovering? Lots and lots of new particles, funny names. And Einstein just said, I would like to understand the electron. Modest man, Einstein. He thought if you could understand the electron, all the rest of it would be rather trivial. And basically, I agree with him. And I'm trying to sell his ideas to you. At the same time, Dirac has his own views, and these pictures embody both Einstein and Dirac's ideas. And the key thing about this picture, this is meant to, well, it's a two-dimensional picture, but you can imagine it sort of rotating in four-dimensional space if you want a four-dimensional picture, but two-dimensional is good enough. This object you see, well, it got two pictures. First of all, there's a curve. Here was, I think I use this fancy gadget. Here is a curve. Now this curve is a unique curve. It has an equation which I won't bother you with. The important thing is it's tangent to this vertical line here, and out there it becomes parallel to this line. It grows, changes from here to here, and the only thing that you vary in there is the scale. Just like a circle of very large radius can become eventually a straight line, this thing here is looking like something curve which, as you stretch it out, becomes more and more like this line. On the other hand, when you go out to the other end, it becomes more and more like that line. And if you rotate this around, you'll get a sort of two-dimensional picture. So out here it looks like a cylinder, and here is this little curved piece which corresponds to this. And this picture is what geometrical model of what I think an electron is, following the ideas of Dirac and Einstein. And I'm going to try and sell you that. It has many aspects to it, but the important thing to remember is that a single parameter, only one parameter, as you alter that parameter, it just changes its scale. At one limit, it goes very much, looks like this. The other end, it's looking like that. But it's all one continuous curve. And so when you want to know what's happening here or there, you can just move along the curve by following the appropriate equations, following geometry. So the part near here, which is, you think of where the central particle lives, and the part furring out there where it's going away a long way, these are linked together in a unique way. And that it has many fun geometrical consequences. So just remember that picture. Pictures are, worth 1,000 words, and here, on a computer they're even easier. So let's now try the next one. Wrong way. Okay. So now I'm going to talk. I was showing you what I think. Einstein asked, "What is an electron?" So I've shown you what I think an electron is. Now let's talk about it. So first of all, let's talk about the physics of the electron. Well, you may not know much about what the electron is. Very few people know what an electron is, but some properties it has. The most important properties are here. The first property is that it has electric charge. That's why it's called an electron. It carries electric charge. And the geometrical underpinning of that is related to this famous circle, which was introduced by Dirac. Dirac was the first person to explain why electric charges come in integer multiples of the charge of the electron. You don't get fractional charges. And that's a fundamental fact of experimental life. And Dirac was the first person to produce an explanation of that, which is still the only good argument. And the only good, all the correspondence to was the fact that the circle has a number, number of times you wind around the circle, is an integer, and that integer is electric charge. So electric charge was understood by Dirac in terms of the topology of a circle, we would say, and that's one of his famous properties. I'll come to that later on. I'm jumping from the physics to the geometry. The physics is clear. It has electric charge, it has a spin. Well, we don't know what spin is in many ways. It's a difficult notion, but people discovered that an electron has a property called spin, which is very important, and searching for understanding spin took them a lot of time. But these are two basic properties which nobody disputes. Now the next two are where I become unorthodox, where I'm making radical statements. And the radical statement here is that in physics there are two kinds of, standard physics, there are two kinds of particles. People talk about what they call fermions and bosons. Don't worry if you don't know what they mean. They're called after Fermi and Bose. You've got the right kind of name, people add on to the end, make you a particle. My name doesn't lend itself that way at all. So Bose and Fermi were very fortunate. So there's the fermions and there are bosons. And the idea is that they come in two kinds, and the fermions have half integer spin, and the bosons have integer spin, and everything is meant to be made out of bosons and fermions. And and the electron is a fermion. But my statement here is that this object, the model of the electron we have, although it's always a fermion, is almost a boson at infinity. When you go along that long cylinder, it's beginning harder and harder to distinguish it from a boson. But it's never actually a boson. It's always a fermion masquerading as a boson. That's my first radical statement. No physicist will agree with me. Well, not yet, but I'm going to try and sell them. So this is a statement I'm making which is liable to get me shot. But that's only one. I'm going to be shot for many reasons, so you might as well go get for a lot of them. Now this idea, as physicists have a notion of symmetry. Symmetry is a very important thing in physics. It underlies the understanding of all particles' nature, but amongst all the various kinds of symmetry, physicists come up with the one they like most of all. They call it supersymmetry. Physicists are very good at propaganda. Super is obviously something you can sell. So supersymmetry was meant to say that with every particle which is a fermion, that there's a corresponding particle which is a boson. There's a symmetry between bosons and fermions, and they should always come in pairs. The trouble is, nobody's ever found them. You look for people in CERN doing big experiments, keep looking hard to find signs of supersymmetry. They're trying to find the supersymmetric partner of the particles we already know. Every particle knows is supposed to, in this theory, have a partner which has the other behavior. But they've not succeeded. And my view is they haven't succeeded because there is no such thing. Instead of that, the single object which is fermion all the way through, but is almost a boson in infinity, is supersymmetry. It replaces supersymmetry. The partner is the long tail of the object at the end. So the single object, which I'm being very radical about, has one bonus. It replaces the notion of supersymmetry, which is experimentally unverified, by something which is much more sensible. So that's my first. I got shot for that already, but now let's go see if I can live a little longer. Let's see. So that was the physics of the electron. I did sort of stray a bit into the geometry, but let's carry on. Now the geometry. Well, the first thing about this model is that the electron is not a point. Traditionally, physicists think, what is an electron? They start off thinking it's a point. And a point is a very difficult notion, actually, because what is a point don't really exist. They're idealizations of something. So it's always a bit difficult. Then they start talking about quantum mechanics, and they get themselves into a bit of a mess. Now, my model, the model I'm trying to sell you, the electron is called an extended object. It's not localized at one point. And the reason for that is that picture I showed you was something with a tail. And the tail is well, it extends the object. The object, you think of it starting off at the one end, but it has like a comet. So it's a long tail. That means it extends into space. And therefore it isn't localized. But if actually, when you look at it carefully, you'll find that its extension into space is quite small, because that tail is very nearly a perfect cylinder, and when it's a perfect cylinder, you can't see anything. So it only extends a small amount. So the model of the electron that I'm trying to sell is that of a small object. And there's only one scale involved in it, because I told you those pictures had only one parameter. And that parameter is a very small parameter, and my second observation, which is radical, is that is due to gravity. My video showed you the importance of gravity. I told you that gravity is a universal force that's everywhere present, because the rest of the universe is there, and whether we like it or not, we live in a gravitational field. Of course, it's a very small field. If you measure a gravitational force in this room or in the lab, it's so small your counter won't show it. I mean, if you jump up and down, you notice the gravity is here as a big object, but if you go down to small levels like the electron and the proton, gravity seems to be totally insignificant. That's why physicists always disregarded it. My argument, this is my radical argument, is that's a mistake. However small is not zero. And when something is not small, doesn't matter how small it is, being non-zero is very important. Remember the difference between a circle and a straight line? A circle doesn't curve, circle curves, a straight line does not curve. Even if the circle is very, very large radius, so its curvature is very, very small. So small you don't see it. It's not the same as a straight line. It has fundamentally different properties. And so my claim is that the gravity means that at a scale of things which are so small you can't see them experimentally, nevertheless, does alter the nature of atomic physics. And that has various implications. Now here, these are we get into technical language. Those of you who know anything about physics will know there's a horrible word called renormalization, which is one of the things that all students study with and that nobody understands, and it's a mess. It gives you nice experimental data, but it's mathematically, philosophically, totally nonsense. Everybody knows it's nonsense. Whereas in the model I'm proposing, that's all replaced by pure geometry. Everything works nicely. There's no misunderstanding. You can develop mathematical theory which is totally precise. And this, I claim, these ideas are really due to Einstein and Dirac. If you interpret them sensibly, and I claim at this end of the day, beauty is triumphant. That conference I talked about beauty, but the next beauty is the thing that's guided Dirac and Einstein all their lives, and I claim that if you follow those ideas to the logical conclusion, things work out nicely. Well, so I've started to tell you the electron. This is my model of the electron, and I've got various colleagues working with me, I'll tell you. But the point is, the electron is that model. If you really understand the electron, Einstein said, you've got the essentials. And my claim is, answering all those fundamental questions about the electron means that we can have a very good, firm foundation of how mathematical physics is built up, which nobody else has. Most ordinary theories are all nonsense, and everybody knows that. They work in terms of experimental data, but philosophically they're all nonsense. I've been shot several times already now today, but I want to make it quite clear how radical I'm trying to be. I hope you realize that. Now, beyond the electron, of course, once you've gotten to the electron, Einstein said, well, the rest of it is exercise for the student. So lots of students here, we go ahead. And it's not hard to work out what direction you should go. There's lots of massive amount of detail, but if you follow the principles, it will lead you in the right direction. So here there is a big, I think, program for people to work out. I've worked out a bit of it, my colleagues have worked it, but we're only just touching the surface. But we have principles which go us in the right direction. And so that is, when you've done that, you have the models. By the way, in my world, the only particles that really exist are things like electrons, protons, and neutrons, and a few other things. I don't believe in all those other particles that people create in the lab and last for 10 to the minus 27 seconds. I just think they're sparks. Which is what they are, of course. Nobody disputes that what you see in the labs are sparks, which don't last very, very long. And then the next question here is a very important one. In physics, conventional physics, there's a lot of discussion about the relationship between experiment and theory, and the whole notion of how do you argument with Einstein and Bohr about the nature of quantum mechanics and so on. Well, I claim that from this point of view, we can understand how quantum mechanics and quantum mechanics are related, and there is a barrier. The barrier is where you are outside an experimental area, you isolate a system, and outside that system, you're an experimenter, and you're trying to see what's happening inside. The barrier is not a God-given thing. You decide where to introduce it. It's at your choice. If you're a sensible person, you put it in a place where it's not going to get messed up. But even so, a bit of information may seep through the barrier, one way or the other, and that's an interesting phenomenon. The other thing I want to point out here is that in physics, people worry a lot about dimensions. And what are dimensions? Well, it's a very difficult notion. I'll come to that later on more. But the point about dimensions, people try to think of dimensions as being built up. You start off with, let's say, space and time. You say there are 4 dimensions. Then somebody tells you need a few more dimensions, and you keep building bigger towers. And where do you stop? Perhaps dimension 10, 11, 12, take your choice. Well, my claim is that's a mistaken view. You're not trying to build a superstructure, you're trying to build an infrastructure. You're digging down instead of digging up. What you're doing is trying to look at things more carefully. When you look at things more carefully, you find they have more degrees of freedom than you had allowed for before, and you call those dimensions. And the more you dig down, the more dimensions you need. In principle, a process doesn't stop. If you think of it as infrastructure, it's much clearer than think of it as superstructure. Now I talk about the real world. Well, I've only allowed 2 minutes for the real world. Because here what I want to just say is that at this stage, you're trying to get beyond the fundamental particles, trying to get to more complicated things, like the hydrogen atom. Hydrogen atom is the most important single thing you construct. Once you build hydrogen, you go on and build the more complicated things. Hydrogen atom is made out of a proton and an electron, but how do they combine? What is it that holds them together? And in my model, we've got a very satisfactory answer for that. So that's how I thought when you get to the real world. And I use the spinors, as I mentioned in my video. Spinors play a very important role, and the Archimedes screw, the double helix. I'm just mentioning them to tell you they're not been forgotten. They're all part of the theory, but I will not pursue them. Now I come to the what people usually call the standard model of physics. The standard model is meant to be about how the various particles behave at small scales. And they forget about gravity. You talk about the various forces that hold matter together. And the theory, which has been very successful experimentally, is called the standard model. And the standard model has very complicated formulas, but it's good experimentally, and it's mathematically totally very difficult to define, and it's all a mess, and the formulas cover pages and pages. It's an ugly formula. Nobody in their senses would really like it, but it seems to work, and people get Nobel Prizes for it, so, you know. But my view is that that's misguided. And there's a much better way of looking at all that, and my approach is based on something quite different. So I'm, again, sticking my neck out here. The difference is that I believe, well, again, I'm not a dogmatist here, but it's conventional from the point of view of physicists that there are 4 fundamental forces. If you ask any physics professor to give a lecture, he said there are 4 fundamental forces. There's the electro force, the weak force, the strong force, and gravity. That's it. There are 4 forces, and we have to work out how they all interact. Well, I claim that actually is the first approximation to the truth, but it'll do. Since it's a standard model, I'll work with it, but I don't think it's as fundamental as they think. I think if you dig deeper, there are more and more layers to this onion. Never mind, let's take 4. Now, where will you get 4 from? If you're a mathematician, there's a nice party of 4 who go together. They're a gang who walk around together, and they are called the division algebras. The real numbers are old friends. We can't do without the real numbers. There's the complex numbers, which we meet in quantum mechanics. There are the quaternions, which are called H after Hamilton, which was his additional step forward beyond complex numbers and played a very important role. And then, actually, rather off on its own, rather the end, there's something, capital O, which are called the octonions. And the octonians, as the number suggests, have to do with 8. And these algebras have dimensions 1, 2, 4, and 8. And they are increasingly lose properties. When you're on the real numbers, you have order. When you're on the complex numbers, things are no longer ordered. And in the quaternions, the algebra is not commutative. When you go to the octonions, first of all, the algebra is not even associative. It's not true that A times B times C is the same wherever you put the brackets in it. And that looks such a mess that people don't like it. Nevertheless, I claim that gravity is associated with the octonions. And that's why it's more difficult than the rest. Well, and actually, interestingly enough, there's a very beautiful theory, a mathematical theory, of something called the magic square. The magic square is, as its name suggests, a piece of magic. And magic should not be decried. These magical things are, well, they have an appeal, which is very deep. This magic square is due to mathematicians, well known, Tietz and Freudenthal, one Belgian, one Dutch. And this magic square is a square that is, well, it's a 4x4 matrix which has these things along rows and columns. It's built up of there's 4 times those things. And that magic square is, I think, useful if you want to understand the interactions of 2 forces. If you want to understand how does electromagnetism interact with gravitation, you look at a particular point in that square, and so on. And one way you get one force is strong, the other force is weak. So you understand all the forces of nature and their interaction by just looking at this magic square. And it's a very beautiful square, and the longer you look at it, the more you like it. One of the features about it is that the octonions here lead to the famous exceptional groups. If you're not mathematicians, you may not know about the exceptional groups, but you probably do know about the platonic solids, the icosahedron and the dodecahedron, things like that. And they're closely related to these exceptional groups. And the exceptional groups are exceptional. They don't fit into a regular pattern. They correspond to particular objects like this. And somehow they are tied up in a very beautiful way with the algebra that lies behind gravity. Well, that's a tall story, long story, rather, not a tall story. Tall stories are not right. But I will just leave it with you there, and we'll carry on. Now here I've got my main collaborators. I must give them credit. Greg Moore, American physicist, whom I wrote a paper many years ago, and then more recently Nick Manton, Bernd Schroers, and Guido Franchetti, who worked with me here in Edinburgh. Nick Manton's in Cambridge. I worked with him for many years. So these are the people I'm working on the present ideas. Now I should say that they don't all agree with me. I mean, we're working together, first we'll have to try to persuade my collaborators. And my collaborators are, difficult to persuade. That's their job. Their job is to question, but I hope I'll get them on my side. And then others. The work I'm doing has many connections with many other people's work all over the world, past and present. I've just listed a list here, starting off with Einstein and Dirac, and many others who have contributed their ideas either before me or with me or after me in the whole area of the interaction between mathematics and physics. It's a vast list. There are millions of people working in this field, and many of the ideas which I've used are derived or come from work of many other people. Many of the ideas are not totally original. Some are, but many are standard. So it's a mixture of well-known things and unknown things. Well, that's the way we go forward. So that's really my closing remark. Now, I should say that in the next lecture, I will dig more deeply into some of the things I've talked about here, this lecture. They're independent lectures, but they're linked. And some of you, if you can stay for the next lecture, you may find out more. Some people may not be here for the first lecture, they'll come out second. But this is, I think, where I'll finish, and I think I hand back now to my chairman, who will close the session.
Thank you very much. Before I open, we have time for a few questions. Before I open to that, I'd like to thank everybody who was involved in putting together today's lecture. There's a lot of technical support at the University of Edinburgh who helped. So I'd like to thank them on our name, in our name together, for arranging this. But we have 5 minutes, so I think there were some very provocative ideas. Are there any questions? I should say, if you have a question, raise your hand. Speak as loudly as you can, but I will repeat the question if necessary. Yes, that's...
You have the colours of the rainbow. Can you expound more significance about colours?
So the question was, you saw the colours of the rainbow in your slogan about spinors and geometry, and you didn't expand on that very much. Could you do that?
Well, I will try. I couldn't resist the colours of the rainbow. They're such beautiful things, and they fit nicely onto the diagram. I think basically the colours of the rainbow correspond to the electromagnetic spectrum, and we were talking about the work of Maxwell and light, physics. So the colours of the rainbow really are the embodiment of some of the fundamental questions to do with physics, and it seems a sort of... But also you can try and describe things in colours which you can't see in just black and white. So it was a kind of half poetic, half genuine scientific allusion. It was serious, but not very easy to define.
Okay, that's another question.
You said that spinors are the square root of geometry. So I know some mathematics. I know as much as what a complex number or a quaternion is. But I've never heard of spinors. So could you explain what that intriguing statement means?
Did you hear the question? And I think that was very clearly enunciated.
Right.
So the question was, explain the statement or comment further on the statement that spinors are the square root of geometry.
Well, I think the question was, what is a spinor? Well, actually, spinors are, in some sense, I think, originally were discovered by Hamilton. As a matter of terminology. Hamilton's quaternions are spinors. They were rediscovered by Dirac and by Pauli. Everybody rediscovers them in their own way. They are the things that you need for various mathematical purposes to understand. Well, going back to Hamilton, that was the real origin. Hamilton discovered really quaternions, and quaternions are the first example of spinors, and they go beyond complex numbers, and they are related to geometry in complicated ways. And when you examine that, you find that you have to square spinors to get into things which are normally geometrical. Spinors themselves don't have natural lengths, but their squares do. Well, the squares have more than natural lengths, because the square of a spinor is not just something with it has a combination of things corresponding to length, area, and so on. All the different things you measure in geometry all together arise when you square spinors. So spinors are, in that sense, the square root of geometry, because when you square them, you get everything you measure. And that you couldn't make more clearer. But understand their meaning, give a definition is one thing. Understand their significance is taking me all my life. And I'm a bit older than you. And I haven't finished yet.
Andrew.
Since physicists looking for particles and finding them, obviously wasting their time according to you, should the government not support ceremony?
I think everybody heard that, but so picking up the notion that physicists are wasting their time looking for particles, should the government stop?
Well, let me say that I've been shot so many times already that I don't think I'll ever say that physicists are wasting their time doing things. They're doing experiments. I've been to CERN, I've seen the fantastic bits of engineering they do, and don't forget the spin-offs. We have the internet, the result of people at CERN. So they're marvelous engineers. They build magnificent machines. They're trying to delve into things of very high energy, and there's no question that delving things of high energy is trying to understand physics at some very small distances. But I think they're totally correct, and they should do the experiments, and they get very good results. But it's a mistake to assume because you've done an experiment which has enormously accurate consequences, automatically it has to be right. Einstein and Dirac said that. They said, I don't care that you get all these very brilliant experimental results. If you've got no fundamental theory understanding, forget it. I want to know what's really there. And I'm on Einstein's side and Dirac's side. Einstein and Dirac died too young. Now, Einstein was just 76 or something, and Dirac was 82. Mere youngsters. They didn't live long enough to get their theories into fruition. Well, I've lived a little longer, and I think the links have been on my side. But I go back to Einstein and Dirac. I claim that all the things I'm trying to talk about are really natural evolution of their ideas with a little bit of nuancing and a little bit of teasing out different combinations together and ideas from other sources. And if Einstein and Dirac were both here, I think they'd be saying, well done, boy.
I saw, was there one more question? Yes, so there's one more question here.
Early on you said that the electrons are fermions and in infinity they become bosons. Can you say a little bit, can you expand on that and say if it predicts anything that you could experience?
So the question was expand on the statement that fermions are asymptotically bosons, electrons are asymptotically bosons, and how one could test that. Is that your question?
Well, I think the point is that that picture, I should say, has a very close relationship with ideas due to de Broglie and Bohm, which were very old, about how you could understand quantum mechanics in terms of something being both a particle and a wave. They talked about a particle and a wave. The wave was called the pilot wave. And they developed a very significant theory which was quite satisfactory up to a point, but it fell out of favour because it didn't need particularly new, and it couldn't go beyond what they were doing. I claim that the things I'm trying to put forward are an improvement or a replacement or an alternative version of what Broglie and Bohm were doing, and that it fits much better with everything both before and after. And the main advantage is not in terms of experimental prediction of small effects. I mean, trying to add another significant figure to 10 decimal places is not worthwhile. You're trying to make improvement to the fundamental foundations and conceptual understanding, which will itself have consequences further down the line. The consequences are not the place you first look for them. Their consequences are elsewhere. So I claim that there will be consequences, but the consequences are not in adding 11th decimal place to something already worked out 10 decimal places. That's what experimentalists do, and that's what theorists do. Theorists try to redefine the theory in a way which is coherent and will have predictions. But the predictions will occur in some different place. So that's where I claim the theory will be tested. But it's satisfactory at the beginning at a conceptual level, which is already, more than most people can offer.
So I can see people are getting braver with questions now, but perhaps one last question, because Michael was very keen on keeping to the time. So there was one question which I turned down. Yes, please.
Yes, this is a question similar to the ones asked before. Do you think that, for example, quarks, you said your model just has protons, neutrons, sort of part of what we knew much before. Do you feel that quarks, for example, were powerful in the way we got like nice experimental results? But will in the end be looked upon as like a philosophical misstep in our understanding of nature?
So the question is about commenting on quarks and whether they are ultimately a mistake in our understanding of nature.
Well, in my model, or our model I'm trying to develop, quarks are present, but they're not particles. They are part of the underlying structure which you can understand and really quite well. You can see how they can be interpreted to make things up, but they're definitely not particles. They don't exist like the proton and the neutron. They are part of the geometrical interpretation, and I have a good idea about how they should be looked at, but they're not particles. And the fact that people can't find these things are very mysterious. These quarks, you can't find them freely. There are all sorts of mystical rules about how they have to live together. And I believe all that's a mistake. The quarks are there in some mathematical sense. They mean something, but they don't mean what people think they mean. Again, it's a radical idea, but if you're going to have radical new views, you better address everything. And I certainly have views about quarks, and the views seem to be quite consistent with the theory I'm working on, and I'm quite happy to debate that over the next months with other people. It'll take a long while to work out. But yes, quarks have not escaped our attention.
Okay, thank you very much. So I'd like to thank Sir Michael again for very stimulating lecture. And there are refreshments outside. You're welcome to stay around to discuss. And then there'll be a second lecture at 11:30, which will be slightly longer. So that goes on till 12:45. Thank you very much.